So our next lecture for electric, gravitational, and magnetic fields, that's the unit 3. We're still on electric fields, and the next lecture is on electric potential energy. This is 7.4, section 7.4 in your textbook. So from the definition of an electric field as a force acting on a charge, it follows that for a given uniform electric field, charge and particle mass, the particle undergoes a uniform acceleration since the force is constant. This ability of an electric field to accelerate charged particles with known conditions has proven useful to physicists and engineers. So if you recall, epsilon, I've kind of related that to acceleration, and this might help your understanding a bit. If we have a constant acceleration, if we have a known acceleration and that acceleration doesn't change, it makes math involved with finding acceleration a bit easier. This is where a lot of our motion equations come from, because they operate with a constant acceleration. Now, we don't usually have a constant epsilon, a constant electric field, unless we use parallel plates or other types of devices that cause that. But in the more natural sense, where we have point charges or charged objects that are not spherical, we have these non-uniform electric fields. So you can imagine how difficult it would be to calculate what it would be like throwing a ball through a gravitational field where the gravity changes multiple times throughout the ball's path. Now, in order to make our math easier, we create these uniform electric fields, and it's not necessarily just to create the math easier, but it gives us a lot of different applications as well. So what you're seeing here is our epsilon is pointed upward, and that epsilon, right? I know it's shown as a capital E, but let's consider it an epsilon. That's like our G again, right? So this is like our gravity. Now that we know that it's a uniform field and it's pointing upward, if we toss a ball or a charge through that, if the charge is negative, it will fall in a parabolic kind of motion. If the ball is positive, it will rise in a parabolic motion. And again, that's the weird thing about this again, is that we have the positive and negative. The charge is something we have to consider, whereas when we're talking about gravity, it's always attractive, so we always have that falling effect. So this is how we're going to look at this, and we can now look at energy associated with electricity as well. So but actually, there's one quick little side discussion here, and it says here that, for example, particle accelerators are used to accelerate particles to speeds near the speed of light. They're also used in a large variety of other applications, including particle therapy for oncological purposes. Particle acceleration is also important in some everyday devices as well. If you have an inkjet printer, the ink moves to the paper. Basically, the ink droplets are charged, and depending on the electric field, the droplets are either allowed to go through to the paper, or they are attracted to a gutter, which kind of deflects those charged ink droplets down and to be collected and used later. There's another application of particle accelerators, these cathode ray television tubes. So on the old CRT televisions, they would basically accelerate electrons or particles and deflect them towards the phosphor screen. So the electrons would then hit different points of the screen, and as they would hit the screen, they would make the screen different colors or different levels of brightness. Now, going back to the energy, if we move a particle through an electric field against the electric field, we've done positive work. Same idea as if I pick up, say, a basketball off the floor and I raise the basketball, I've exerted a force and I've gone a distance, so my work is the force times the distance. The same is true in an electric field. We worked against gravity by picking up the basketball. In an electric field, if we move a particle from one location to another against the electric field, we will be doing work, positive work. Now this depends, actually, I guess I shouldn't say against the electric field. It also depends against the charge as well. So if we're moving a positive charge, if we're moving a positive charge against the electric field, so you remember the electric field lines, they radiate outward for a positive charge. So if we move a positive charge against the field, so we're moving a positive charge closer to the source of the electric field, we will be doing work, positive work. And if we allow the positive charge to move away from the electric field, we are doing negative work. Then the opposite's true for a negative charge. It gets a bit more confusing with the fact that we have positives and negatives, but the concept is the same. And actually, I should point out as well, the electric force, Fe, is equal to Q times epsilon. That, again, I've said this earlier, but that's the same, you can think of it the same as F equals ma, where m is the Q. So instead of mass with gravity, we have charge, which is Q, and epsilon is the A, the acceleration. So instead of the acceleration, we have the epsilon. So now I'll read through this because this talks about work. I've already kind of explained it, but it says, suppose this charge moves at a certain distance, delta d, starting at point A and ending at point B. If we assume the displacement is parallel to the electric force, then the work done by the electric force on the charge is work equals force times distance. Same equation, but now it's electric force. So we can now define the electric potential energy. So this is E, capital E, which is the energy stored in the system that can do work on a positively charged particle. So you would know that the change in the potential energy associated with this type of force is equal to negative work. So the electric field loses energy doing work on the particle to accelerate it. So electric potential energy, please copy this down. It's the energy stored in a system due to a charge in an electric field. So if the electric force does an amount of work W on a charged particle, the change in the electric potential energy is, so the change in electric potential energy is negative work, which is negative force times distance. And because force is Q times epsilon, it's negative Q times epsilon times delta D. And that's the equation that we're going to be using. So I'd like you to copy this down. And copy down all of the definitions as well. The note says that electric potential energy is stored or lost through the potential effect of the electric field on an electric charge. So now let's talk about electric potential energy difference. So if a positive charge Q is moved from B to A against the electric field by an external force Fa, then the work done by the electric field on the particle is negative. So in other words, a positive amount of work is stored in the system. So this energy loss is usually shown as a decrease in the kinetic energy of the particle. And as the charge moves from A back to B, the process is reversed. So the energy stored in the electric field in the particle system is taken out of the system. So now the electric field does positive work, and this increases the kinetic energy of the particle. So as the particle is moving, it's increasing in kinetic energy or decreasing. Consider it this way. If I throw a ball up, I give it an initial VI and an initial kinetic energy. It starts to slow down as it works, it's moving against the gravitational field. So it starts to slow down. So the work is represented as a loss of kinetic energy. And if I drop a ball, its initial velocity is 0. It gains its energy as it moves through the gravitational field. It's the same idea in an electric field. So it's good to remember the connection between the electric field and the gravitational field. They operate the same way. The difference is in the electric world we have positive and negative charges. And we also have positive and negative electric fields, whereas in gravitational fields we are always looking at an attractive gravitational force. So that's the gravity's going down. So let's look at some of these problems. Here it says a charged particle moves in a uniform electric field. So for a proton, and a proton has this small charge of 1.6 times 10 to the negative 19. We'll get into that in a little bit. It says calculate change in the electric potential energy when the magnitude of the electric field is 250 newtons per coulomb to the east. We have the starting position, we have the final position. So we're looking for the change in the electric field. So that's delta E, the change in the energy in the electric field, so the potential energy. And that equation, because we're dealing with a uniform electric field, on your formula sheet there's an equation that says for parallel plates. It is for parallel plates, but it could also say for uniform electric fields because the electric field between a parallel plate is uniform. So this is negative Q, which is our charge, times epsilon times delta D, the distance traveled. And this is designed so that we can substitute our Q value in with its charge. So that's something to consider when you're using this equation, which means that our Q we have to write as positive 1.6 times 10 to the negative 19. Our epsilon is 250 newtons per coulomb, and it goes to the east. And our distance traveled is the difference between our final position and our initial position. So in our calculator, we have 1.6 times 10 to the power of negative 19 times 250 times 3.9 minus 0.4. Now I'm supposed to make this whole answer negative, so I'm going to hit the equals, and I'll negate it, and then I will hit this button to see what my significant digits are, or rather to see what my answer is in scientific notation. So it's 6.0 times 10 to the negative 17, negative 6.0 times 10 to the negative 17, and that's joules because we're looking at energy here. Now the implication is we've lost energy in the electric field, which means that the proton has increased its kinetic energy. So this is a situation similar to a proton. It's basically speeding up. So if we dropped a ball in a gravitational field, the ball's velocity would increase. It would speed up, which would we could think about that as a loss in the gravitational energy or the gravitational field. But we show that negative energy, that change in energy being negative, means that the proton has sped up. So let's look at the next part of this problem. It says here a charged particle moves in a uniform electric field, and calculate the change in the electric potential energy for an electron in the same field. Now, if this was an electron, I won't do this, but the difference here would be that this term is negative, and then this becomes positive. So if this is negative, we have a negative times a negative. That implies that, or that gives us a positive, which means it's the same amount of energy. Here, the electron would slow down, because if the electric field gains energy, that means that the electron was moving against the electric field, so it would be slowing down. It would be losing kinetic energy. Here's a problem. It says using the law of using the law of conservation of energy, calculate the final speed of a proton, the proton in part A of question 1 for the given displacement. Assume the proton starts from rest. So here's where we're going to use conservation of energy, and this is kind of interesting because we can actually use the same kinetic energy equations we use for larger objects as we can for the smaller objects like protons and electrons. And it has a gain. This is our gain in energy for the proton. So it basically would have an EK of 1/2. Sorry, it starts from rest. So we have to consider that its kinetic energy before was 0. So the energy was lost here. So any gain in energy has to be equal to this. So that's our conservation of energy. So it's 1/2 m v squared. And the kinetic energy gain, we're looking for V. So that is V equals the square root of 2 EK over M. And our energy was, we could take the absolute value of this because it's a gain of energy for the proton, 6.0 times 10 to the negative 17. The mass of a proton is on your formula sheet. It shows up in that top left corner, or top right corner, 1.673 times 10 to the negative 27. We should always use the 4 significant digit value because it's very accurately measured. So using this and putting this into our equation, we end up with, so I'm going to get the square root, so I'll put this in brackets. So 2 times 6 times 10 to the power of negative 17. Divided by 1.673 and divided by 10 to the negative 27. I'm going to close the brackets, raise this to 0.5, and what I end up with, I'll switch this to scientific notation. I end up with 2.6789, so that, if I'm looking back, I have 3 significant digits for the proton's mass. They only told us to use the 3 significant digits, but looking back at the original question, I have 2 significant digits as my lowest, so I have to report as 2 significant digits, which means this is just a 2.7 times 10 to the 5 meters per second. And this would be going in the east direction. So one other question before we finish off, and this says determine the initial speed of the electron, and the electron would be using this as well. So it says that assuming the electron comes to rest after the same displacement. So here, the electron comes to rest, so its EK has to be totally lost, which is 1/2 mv squared, which is V equals the square root of 2 EK over M. The mass of the electron is, on our formula sheet, it's 9.109 times 10 to the negative 32. So 9.109 times 10 to the negative 31, sorry. I think I said 32. So this works out to 2 times 6 times 10 to the negative 17 divided by 9.109 divided by 10 to the negative 31. I don't know if I did that properly, but this is the square root. It should be 1.1 times 10 to the 7 meters per second. So that was its initial speed, and it slowed down while it passed through that electric field.